There are a host of other examples where classical physics, fails to explain, things that you can measure in the laboratory. For example, the wide range of conductivity. So we know that conductivity of an electrical conductivity is due to the motion of free electron within an object. Now, if I compare, say, the conductivity of silver, to the conductivity of, say, quartz, the silver conductivity is, its magnitude is many orders higher, bigger than the conductivity of quartz. And classical physics is not able to, explain this huge range of, of conductivity, right? So there are lots of examples like this. Okay. Now, historically, the place where quantum mechanics, reared its, I don't want to say ugly, I want to say beautiful head. Was in the heat capacity of diatomic gases. So for example, H2. So from our course in StatMech, we saw that the heat capacity of diatomic gases is given by 7/2 of N of Kb, where N is the number of molecules and Kb is the Boltzmann constant. And so we can understand this as we have three translational degrees of freedom. So each translation degree of freedom contributes, say, half. So we get 3/2 of NKB. And then we have a vibrational, mode, and that gives me 1 of NKB. And then we have 2 rotational degrees of freedom, which gives us another N of Kb. And then, this basically makes up the 7/2 of N of Kb, right? So, these are all results from the relevant equipartition theorems. Okay? So this is basically the prediction of classical statistical mechanics, that the heat capacity should be 7/2 of N of Kb. But experimentally, what was observed is something very different. Experimentally, the heat capacity in certain units, was observed to be at very low temperature. So this is a logarithmic scale. So this is a log of some T, and this is the heat capacity. So this is, say, 1, this is 2, sorry, Yeah, that's the way. This is a 1, and this is 2, this is 3, and this is 4. And then what happens is that at very low energy, this is all the degrees of freedom are sort of frozen. Only the translation degrees of freedom are there. And then at some energy, the rotational degrees of freedom are, some temperature are turned on. And at some higher energy, the vibrational degrees of freedom are turned on. And to understand this, we need a lot of quantum statistical mechanics. Okay, so this is 3 halves, and this is 5 halves, and this is 7 halves. So this is the first case where evidence of a quantum nature of the world came across in a direct way, but no one in 19th century was able to explain this. Quantum mechanics was not that, there was no simple assumption that they could make which would lead them to uncover the quantum nature of the underlying physics. So people, that was a missed opportunity. This was only explained, after the discovery of quantum mechanics. Okay. Okay, so that's another one. Another evidence from the 19th century was the evidence coming from the Gibbs paradox. And those of you who have done my course, you learned about the Gibbs paradox, where it points to it's how if you calculate the entropy of the mixture of two gases, depending on your point of view, it can be very different. However, the paradox is resolved if you assume that all the particles involved, all the particles of the same type involved are indistinguishable, right? So the Gibbs paradox, hello?
I have a question about the earlier graph.
Yeah.
If quantum nature was not true, what would this graph look like?
No, it will just be this.
Okay.
Yeah. So the Gibbs paradox, what it does is that it points to an important fact in quantum mechanics, which we will discuss later in the course, is the fact that similar particles, such as electrons, are indistinguishable. Okay. So, for example, suppose that we have a black box, and we throw in, say, 2 billiard balls. Okay. So there's billiard ball A and billiard ball B. And then suppose that these two balls come out in that direction. Okay, so now, if the 2 billiard balls look exactly the same, and we don't have enough information about their velocity here and here, then there is no way for us to say which billiard ball is which are A prime and B prime, right? You know, A may be A prime, B may be B prime. But, you know, but we cannot say that, but we can safely say in classical physics that A prime is either this guy or this guy, okay? In quantum mechanics, if A and B are two electrons and you send them into some black box and they come out, in principle, there is no way to say, there is no meaningful way in which you can say A prime is either this or that, and B prime is either A or B. Okay, and what it does is that it actually, you know, affects the way you count things, count the number of possibilities in a quantum system. So it affects indistinguishability of particle. You know, affect the statistics of quantum particles. Okay. And in 3D, there are two types of statistics: the Bose statistics, which was discovered in Dhaka University, and the Farabi statistics. Okay. So the indistinguishability of quantum particles has, you know, real experimental ramifications. Okay. So these are like, we can just go on and on and on about how classical physics fails and how we need quantum physics, right? But historically, the place where we first made a concrete, say, hypothesis about quantum mechanics was in the analysis of the black body radiation. Okay. The black body radiation, the analysis of black body radiation led to a disaster known as the ultraviolet catastrophe. Okay. And it's the analysis of the ultraviolet catastrophe that led to the first inkling that there might be a different kind of physics altogether at the small level. I mean, the inkling was there before, but no one could come up with a very precise formulation or formula that would explain how to deal with it. It was Max Planck who, when he was trying to solve the ultraviolet catastrophe, came up with the first you know, idea for quantum mechanics. Do we have any questions so far?